All right, this is 5.5 part 3. We are now looking at the fundamental theorem of algebra and then linear factorization theorem. So let's see what these two theorems say. If every polynomial function of degree 1 or more has at least one complex zero. Remember, complex just means a plus bi. So it's saying that it could be a real zero, it could be an imaginary zero, it could be a combination of the two. So it doesn't matter if it's real or imaginary, but every polynomial has at least one zero. From this, we can conclude that a polynomial of degree n has exactly n complex zeros if you count for multiplicities. So let's say your polynomial has degree 3, then you should have 3 complex zeros. So your zeros could be 1 and 2 multiplicity 2. So then that 2 is counting twice, right? So 1, 2, 3 zeros. Or your zeros could be I, negative I, and 2. You're going to have 3 zeros if your degree is 3. Let's look back up at this example here. The degree was 3. And how many zeros did we have? 3. Exactly what the theorem is saying. Okay, the linear factorization theorem. A polynomial function will have the same number of factors as its degree, and each factor will be in the form x minus c, where c is a complex number. Okay, so it's saying that you will have the same number of linear factors as the degree, which makes sense because we know every zero corresponds to a factor. If I have I as a zero, then I have x minus I as a factor. If I have 3 as a zero, then I have x minus 3 as a factor. And so for every zero, you're going to have a factor, which means again that the number of factors is going to be equivalent to the degree. That's what both of those are saying. All right, find a polynomial function that satisfies these conditions. So on this problem, you are told that you have 4 as a zero of multiplicity 3, and then that f of 2 equals negative 24. So what are you going to do with that information? Basically, you're going to write this 4 back into factored form. So that is x minus 4. And then because it has multiplicity 3, we're going to cube that, right? And so how many factors does this polynomial have? It has 3 factors. I just wrote them all together with a cube. Now I don't know what my coefficient is here, so I'm just going to call it a. And that's the purpose of them giving us that when x equals 2, y equals negative 24. So that's 2 comma negative 24. So we're going to plug into, for x, negative 24 for y. And that allows us to solve for that coefficient a. Okay, 2 minus 4 is negative 2. Negative 2 cubed is negative 8. So we'll divide by negative 8. So a equals positive 3. Okay, we'll plug that a back in for that 3 back in for a, right here in the original. So 3 x minus 4 cubed. And there's your polynomial satisfying those conditions. Now you could be asked to multiply all of that out, do x minus 4 times x minus 4 times x minus 4, distribute the 3, but I think we're pretty solid with our polynomial multiplication now. So you would be able to do that. All right, number 13. This one has zeros of -1, 1, and 0. So again, I don't know my coefficient, but I've got x plus 1, x minus 1, and then x minus 0. Oops, not 10, 0. Which is just x. That is just x. And so we usually write that x in the front. So I'm going to put ax there. Now I can plug in my 2 for x and my 3 for y to solve for a. Okay, so that gives me 3 equals 6a, so a equals 1/2. So plugging that back in for a at the beginning, I've got f of x equals 1/2 x, x plus 1, x minus 1. So if I have 3 zeros, and which means I have 3 factors, that means that this is a polynomial of degree 3. Just tying that back into those theorems. This would be a polynomial of degree 3. All right, number 14, find the zeros of the polynomial function and write the linear factorization of the polynomial. Okay, so this goes back to what we did in part 2. We could use the rational zeros theorem to find our rational zeros, but if you look closely at this one, actually you know how to factor this, so you have an option here. You could just go ahead and factor it, or you could do your rational zero theorem, do all that work to find your zeros using synthetic division. How about, since we noticed we could factor this, we just factor it. Unless it tells you what to do, what method to use, you're welcome to factor if you're able to. So just factoring this by grouping, there's what I get. All right, but it asks to write the linear factorization of this, which means I can have no x squared, x cubed, and so on. All of my factors just need to be x plus a number or x minus a number. So what I need to do is factor this. Well, I'm unable to factor that because it's not the difference of squares. And the difference of squares is the only way you can factor binomials that involve squared terms. So what I'm going to do is just find my zeros first. So set each factor equal to 0, solve for x. Okay, we're going to take the square root, right, to solve for x here. Don't forget the plus or minus on that. Okay, the square root of -1/3. So first of all, the negative can come out and become an I, imaginary. And then the square root of 1 is 1. I guess I can break this up for us. Square root of 1 is 1. I'm going to put the I on top here. The square root of 3 cannot be simplified. Now you could rationalize this, remember, by multiplying by the square root of 3 on the top and the bottom. So that's I square root of 3 over 3. Square root of 3 times square root of 3 is 3. Okay, so those are your other 2 zeros. This is polynomial of degree 3. I have 1, 2, 3 zeros, 3 zeros. So I'm going to go ahead and write out my zeros for part of my answer. 3, I squared root of 3 over 3, and negative I squared root of 3 over 3. Now writing the factorization, I'm just going to take those 3 zeros and put it into factored form. So x minus 3, x minus I squared root of 3 over 3, and oops, I put a comma, and then x plus I squared root of 3 over 3. Sorry, that got a little messy there at the end. So these are your 3 zeros, which we got by setting our factors equal to 0, solving for x. And then we just took those zeros and put them back into factored form to get the linear factorization. All right. Now the complex conjugate theorem. If f of x defines a polynomial function having only real coefficients, and if z equals a plus bi is a 0 of f of x, where a and b are real numbers, then z equals a minus bi is also a 0 of f of x. So this, with the bar on top, means conjugate. Well, that won't fit there. That is that's saying the conjugate of z. Okay, so when so this is the complex conjugate of z, a minus bi. Remember, all that changes is the middle sign when you're getting the conjugate, the complex conjugate, or the conjugate of a radical number like 1 minus the square root of 2. The conjugate is 1 plus the square root of 2. And so in either case, the conjugates are also going to be zeros. So if a plus bi is a 0, then a minus bi is also a 0. And you can actually see that in the example that we just finished on the previous page. You see that we had I squared root of 3 over 3, and we also had minus I squared root of 3 over 3. So if the positive is a 0, then the negative is also a 0, and vice versa. Okay, so if one of them is, then the other one also is. The conjugates come in pairs. The complex numbers come in pairs. All right. So same thing that we did on the last page, but this time we've got complex or imaginary numbers as zeros. So to find the polynomial, this time it needs to be in standard form, and you'll see why. That satisfies the given conditions. So zeros of -4 and 2i. So we're going to put that back into factored form. So that's going to be x plus 4, x minus 2i. Now if 2i is a 0, then we also know that -2i is a 0. That's the conjugate of 2i. So then I have x plus 2i. Now we are going to, on these problems I should have specified, we're going to assume the coefficient is 1. Okay, so no solving for a here. I didn't even give you information to solve for a. So we are just going to leave it at that. But I can't leave it like this because this polynomial has imaginary numbers and we don't want that. So we're going to write this in standard form by multiplying everything together. Now always start by multiplying the two complex, or the ones with imaginary numbers, multiply those conjugates together first. That way the imaginary parts will disappear. When you multiply conjugates together, factors with conjugates together, the imaginary numbers will disappear. So we're going to have x squared plus 2xi, or 2ix, doesn't matter, minus 2xi minus 4i squared. Okay, let's combine like terms. So notice these two terms in the middle cancel, and I squared equals -1. So this term becomes plus 4i. You're multiplying -4 times -1, so that becomes plus 4. So plus 4. All right, now that actually made it a lot easier. Now we're going to multiply those two together. So x cubed plus 4x plus 4x squared plus 16. All right, so there's your polynomial. I'm going to write it in standard form by rearranging the two middle terms so that my degrees are in descending order. So f of x equals x cubed plus 4x squared plus 4x plus 16. Okay, same thing on number 16. So I've got zeros of 2 and 3 plus I. Well, if 3 plus I is a 0, then 3 minus I must also be a 0, because those conjugates come in pairs. So I've got x minus 2, x minus 3 plus I. I'm putting that in parentheses so that we remember to distribute the negative. And then x minus 3 minus I. So because, remember, this is always going to start with a minus here. X minus your factor. So x minus 3 plus I and x minus 3 plus I, and then x minus 3 minus I. And then I'm going to first distribute those negatives before I start foiling. Distribute those negatives. All right, now we're ready to FOIL. So remember, start by multiplying those two together. The ones with conjugates, multiply those together first. Okay, now we will simplify this, obviously, by combining like terms and remembering that I squared equals -1. So I've got x minus 2 still here at the front. Still got x squared. Now I've got this xi minus xi cancels. -3i plus 3i cancels. My negative I squared, that's -1, which becomes +1. Okay, so I'll combine my -3 and -3x, so -6x. And then 9 plus 1 gives me 10. All right, see, when you multiply the ones that are conjugates together, all of those imaginary numbers disappear, and it actually simplifies very nicely. Okay, and then we'll FOIL this last part together. Just distributing the x first. And then distributing the -2. Now I'm running out of space here again, so I'm gonna zip up here to combine like terms. And then we'll be finished. So I've got x cubed minus 8x squared plus 22x minus 20. Okay. Factor the polynomial given one of the zeros. So we've done problems like this earlier where you're given one of the zeros and you want to be able to factor this using that. And what we did was we divided this zero out first using synthetic division. So I'm going to do I, 1, I'm skipping the x cubed, so I need to put a plus 0 x cubed, 26, 0x, 25. Multiply, add, multiply. I times I is I squared. I squared equals -1. I times 25i is 25i squared, and we know I squared is -1, so that's 25 minus 25, which gives us 0. Obviously, if I is a 0 of this, we should have a remainder 0 there. Okay, so now we have these are our new coefficients. Now I'm not going to write those out because obviously that is yucky, and we still couldn't factor that. So what we want to do, actually you could factor that. Let's see, we'll play around with it. So you could continue this and do -i as one of our other zeros, right? And you could do -i here and use 1i, 25, and 25i as your new coefficients. So we'll do that first. Okay, so I got 0 again, obviously, because I know -i has to be one of my zeros if positive I is one of my zeros. Okay, and then I'm left with x squared because I've divided twice, so my degree is going to go down by 2. So x to the 4th, this one's x cubed, this one's x squared. 0x, and then 25. And we can't factor that, but we can set that equal to 0 and solve for x. So x squared equals -25 square root plus or minus. And the square root of 25 is 5, and the square root of that negative gives you an I. So those are your other two zeros. Those are your other two zeros. We're just being asked to find the zeros here, so now we have all of them actually. We've got I, -i, and then our plus or minus 5i. So x equals plus or minus I and plus or minus 5i. So again, we started with a polynomial of degree 4, and how many zeros do we have? 1, 2, 3, 4. Those plus or minuses obviously count separately. One's positive, one's negative. So we have 4 zeros, degree 4 polynomial. And then if we put those in a factored form, we would have 4 factors. Now let's see how we could have actually factored this just for fun. So this would be x cubed plus I x squared plus 25x plus 25i. And so we could factor this by grouping. I would factor out the x squared, be left with x plus I. Factor out the 25, I'm left with x plus I. And so then I would have x plus I and x squared plus 25. I would set each of those equal to 0 because that's what we're looking for, right? We're looking for the zeros, which is where the polynomial equals 0. Okay, and then I would get the same two factors, x equals negative I, x equals plus or minus 5I. So either way, either using synthetic division to take out the negative I there, divide by that 0, or by factoring on this one, I could have got my other two zeros. All right, and that is it for part 3.